Just revisiting this model again in light of some new data and some interesting introspection here. So just to recap, 25 million population, immunity is at 70%, which is what I had before. 20% of people need hospital, so 20% of the immunity level is 3.5 million people in Australia would pass through the hospitals till we hit the immunity. Average stay in hospital is 15 days. Beds, I've set at 100,000, which is at the moment at 60,000, but with a plan to go to 90 plus thousand, and that equals 525. Okay, that's just the mathematical truth. Now I was wrong about this. Apparently we only need 60%, so that drops the number to 15 million. So 15 million people, which is only 20% of the 15 million, only 3 million people will pass through the hospital. All the numbers staying the same. It's 450 days till we've got immunity. Mathematically, that's just the truth. Total peak infections are at 500,000, so that's 20% need beds. The rest at the peak maximum is 500,000 people simultaneously affected at any one time over that period of time. The rate that equals is a ridiculously low. If you're going to push everyone through 100,000 beds, reverse calculating, it's 1.75% a day. Currently, we've been on 5.2% a day based on nearly a week. So we're flatlining here. Our rate of spread is flatlined 5.2, 5.2, 5.2, 5.2, 5.2 with the current measures. So if we let it run, right, so I don't believe that it's possible, there's separate reasons for this where we could squash it down to 0. So the other option is just to push through with immunity with giving people the maximum cover. In this model, something will have to change. So if you say, okay, that's given, 60% is needed for immunity, maybe you could reduce it that only 15% of people required hospital with some treatment or some drug, and that will reduce it to 337 days through 100,000 beds with days in hospital 15. And that rate would be still half what we've currently got. So the measures, the social measures, would have to be double as good than the current rate at 5.2. So maybe we say, all right, maybe the drug not only changes the percentage of people that need to be in hospital, maybe also the drug also reduces the days in hospital to maybe 10 days in hospital is the average stay. So you can push more people through. Okay, we can get to 225, but you'd have to control the rate of 3.5. For 225 days, you'd need to control your rate at 3.5. Okay, we wanted to get it at least where we are now. To get to 5, we would need, let's put it into an experiment, maybe if we upped it to 150,000 beds. That's what it would have to be. So if we can't change that number, 15% of people require hospital with an average stay of 10 days in hospital with 150,000 beds. You would be over in 150 days and the rate would be the same locked up as we are at the moment. Nothing less, nothing more, maybe less, but not more. And that's very, very conservative. Very, very conservative. So what I want to do now is another little trick that I've got here is, let me just back out all of these sort of changes. Back to these numbers. Let's do what is called a Monte Carlo simulation. So I'm going to start my risk solver here, and I'm going to put some values in here because this is just all just theoretical at the moment. Let's actually add some distributions here. So we know that, let's leave that at 60. We're not going to change that. Could be, I don't think it could be lower. 60 sounds like a conservative number, but let's say we'll add a distribution for 20%. So what I mean by that, let's make a guess in a PERT style. So we say 20% is a maximum possible, requiring most likely, let's start here, most likely it's, say, maybe 17% requiring hospital with a maximum 0.2, but it's possible maybe we can get it to 10, right? So it creates a distribution like this. So maybe 10%, we'll write down, that's a relative probability. Sorry if I'm losing some of you here, this is very statistic, but bear with me and you can see where this ends up. 2 maximum, so they're generally around here, and some versions will be down here towards 10%. Okay, that's our first distribution. Days in hospital, add a distribution. Okay, another PERT style. Maximum days in hospital, we'll keep the maximum at 15. I don't think that's the data that I've got. Maximum 15. Likely is maybe they'll get better at getting people out of the hospital faster, so maybe they'll get it down to 12. Minimum, let's say even 8. Don't see it being much less than 8, so it's quite symmetric. There'll be values across here. Okay. Next one's a bit difficult, but we'll put in a value, add a distribution. Again, a PERT style distribution with a maximum. You know, maybe over that period they can somehow crank it. I don't think it's possible to. 200 sounds a bit unrealistic. Let's say 175,000 beds. Likely they'll get to what they're saying they will in a year, 94,000. The minimum, if they don't reach there, maybe they'd only get up to maybe 80,000. Right? So that becomes increasingly more unlikely. Right? So that's our 3 distributions. And as an output okay, one more distribution, which is the death rate. So output, and add one more distribution for death. PERT style. So maximum, let's say it's a 3%. Okay, likely, I think we're going to have something like a 1% death rate. Okay, 0.1, 0.03. Doesn't like me doing it in the wrong order. 0.03. Maybe 0.05 possible. Minimum, sorry, I'm making a mistake here. Likely 1, maximum 3.05. 0.5%, and we'll get maybe bad at 3% as a death rate. Right, so there's your inputs, output variables. Okay, I want to check total days till it's over. I want to check deaths. It's an output variable. What else do I want to see? Let's just try what the rate will end up being. So we're tracking 3 output variables. So what this is going to do is, I'm going to run it across 500 iterations. So the computer, the application, will pick random values that in frequencies that follow these curves. So more likely find values across the peaks of these, and less likely finding values at the bottom of these. And then while it's doing that under each of these 4 input variables, it will track output variables to see how they're distributed. Okay, I don't want to spend too much time explaining it, but maybe from the output you'll see. So away we go. Let's let it run 500 simulations. It's tallying up all the results, and we will get these outputs, right? So that's finished. Let's start with the second last one, output. So it's saying the minimum, the mean 187,000 deaths, the minimum possible 78,000 deaths, with a maximum of 400,000 deaths. So that's the range. So these are the relative probabilities of each of the different scenarios given those inputs. So the mean, about 187,000 so 180, so around here, right? That's the mean. If you look at percentiles, you can say, look, let's just look at the downside. So 83 was an absolute 1% chance of getting 83. There's an 81% chance of 83,000. There's a 3, so you got to add up. That is less than 88,000. There's a 10% chance that it's under 108,000. All right, so you can see how this is going. All right, 10, that's deaths. 20% chance that's 127,000 deaths. Okay, let's go back. Let's look at the days. All right, the low minimum 136 days, best case. Worst case 464 days till it's over. All right, again, let's look at the percentile. So let's look at the minimum only at the moment. There's a 1% chance it's over in less than 163 days. A 10% chance it's over in less than 200 days. And this is what the real data, this is the real data here. There's a 20% chance it's less than 228 days. What was the last one we're looking at? Was the rates of spread. This is the depressing thing here is, you know, we have to have really low values here. Now, I've got some ways that this can transpire to get low values here, but I'll leave that for another video. I think this one's been long enough. Hope this has not been too complicated and you have found this interesting as always.